All right, folks, it's time for our favorite podcast, Cut to the Chase. Here with me right over here, Dr. Adam Leibovich, professor of physics at the University of Pittsburgh and recently appointed director of Pittsburgh's Quantum Institute, a collaborative effort of researchers looking into quantum science in the Pittsburgh area, all working together, different schools, collaborative effort. Today, what we're going to talk about is the James Webb Telescope, which finally has released its first images. We're going to go through those images. We're going to talk a little bit about what's going on, what the mission is, what's so interesting about this project, and where we are right now, where we might go to with this information. How are you doing today, Adam?
I'm doing great. How are you doing, Greg?
I'm doing great. You know, it's very, very complicated, lots of information. So it's kind of, I'm just going to throw out a couple basic facts, then we're going to move into the images. I'm going to ask questions and be quiet. Okay, so James Webb, why was it named James Webb? He was the second NASA administrator. He led the mission to the Apollo mission to the moon. This telescope was actually, if you watched and listened to our previous episode on the James Webb Telescope, which we did, I think back in, was it Christmas? Was it right about the launch?
Around there, yeah.
All right, so the launch, this telescope was actually launched. It's not like on the ground in a big telescope, but it was launched on Christmas. I will drop the link that will allow you to go back and actually watch that launch, as well as the progress of the telescope, where it is, its speed, all those kind of interesting things. The JW, I'll drop the link, but it's basically the James Webb Telescope YouTube channel is what I'm going to be dropping. Where is it right now, Adam? Where is the telescope?
So the telescope's at a point which is called the L2 point, which is a point in space, which as the Earth moves around the sun, this point stays fixed relative to the Earth. So it's being essentially dragged around the sun. In this point, it's sort of shielded from the sun by the Earth, which removes some of the excess light that it doesn't want because it's not looking at the sun, it's looking out into deep space. And it is very far away, much farther than the moon, and it's one of these interesting points that gravitationally is convenient.
Okay, so what I'm seeing is 1.5 million kilometers from the Earth is where it's located at the L2 orbit right now, which is approximately 4 times further away than the moon.
Something like that, yeah, that sounds about right.
Okay, and it's so far away that if anything breaks on it, there's nothing we can do.
That is correct.
All right, and this launch took approximately 1 month to get to the L2 orbit from what I'm reading. And the telescope, how big is it? Well, do we have an idea?
It's extremely big. There's many different aspects to the telescope. The mirror itself is made up of a bunch of hexagonal mirrors, which they aligned and first unfolded because the whole telescope was folded up. They had to unfold it and then align these to make essentially one very, very large mirror. And then there's also a big, essentially heat shield to block off any excess heat that might be hitting the telescope so that it can observe the very faint light that it's trying to do.
Okay, so what I've seen is it's approximately the size of a tennis court and it weighs about 6,500 kilograms.
Yeah, so the sunscreen is about the size of a tennis court. The mirror itself is smaller, but it's still an extremely large mirror.
All right, and so people that talk to me say, hey, what big deal? We had the Hubble Telescope. What else could this actually do? How is this different than the Hubble Telescope in terms of not the technical specifications of how it differs, but like what can it do that the Hubble Telescope cannot do, and why is that significant?
Well, it can do a lot more than the Hubble Telescope. Not getting into the details, the main thing is it collects much, much more light than the Hubble Telescope. And when you are talking about astronomy and you're collecting light from far off in space, the more you can collect, the better you can do. So it can see deeper, it can see further, it can see better spatial resolution. And it also is looking at different types of light than the Hubble's looking at. So it is designed to do things different than the Hubble is. And I don't have the website loaded up, but I mean, you can go online and look at comparison pictures from the Hubble and from the James Webb, and the James Webb just blows Hubble out of the water.
All right. So the first reviews that I'm seeing is that it's actually outperforming expectations.
It's performing unbelievably well. They were able to get it there. Just was a difficult thing to begin with. They were able to get it set up to actually observe light, which again was not an easy thing to do. And the images that are coming in are spectacular.
All right, and from what I've read, it's designed to be orbiting for 10 years.
Right. So I mean, it has a limited lifespan because it does need to use a little bit of rocket fuel to stay in position. Not too much, but a little, and it doesn't have a ton on there. So once the fuel runs out, it won't be usable anymore. It also will get hit by little bits of space debris, rocks and little asteroids and such. It already had one impact. It doesn't, it's designed to be able to still work even with those impacts, but over time it's going to get beat up and then it will run out of fuel. So eventually it will reach the end of its lifespan.
All right, but what I've read so far is that although it was designed for 10 years, now they're expecting that it's going to go beyond that.
Well, one of the nice things that happened, or fortunate things I should say, is the launch went perfectly, which means that they did not need to use some fuel to do orbit corrections. And so they have more fuel than was designed. So they always have some extra supply, in this case of fuel, so that they can still do what they want to do and have the lifespan. They have extra fuel, so it will last, it should last longer than those 10 years because they won't run out of fuel as early as
anticipated.
Exactly.
Gotcha.
Thank you.
All right. Here to help. I'm here to help.
Yeah.
All right. We cut.
I needed this morning.
I know.
I only had a small cup of coffee.
Yeah, no, I had half a cup of coffee, but in any event, all right. So now like a lot of these kind of, I'm going to just say things. I know it's not the best word, but there's a mission here.
Mm-hmm.
And what is the mission? What are the objectives of sending this thing out, which I'm sure cost a ton of money
Mm-hmm.
and had cost overruns and
Mhm.
problems along the way?
Yeah, delays, lots of delays.
Lots of delays. All right. So what's the mission?
Well, it's doing many different things. There's lots of different pieces to the mission. So one is to look back at the earliest, farthest back in time that we have been able to observe so far with a telescope like this. So it is designed to be able to see further back in time than Hubble could do, or any other telescope for that matter. It is designed to be able to look for gases around exoplanets. It's designed to be able to study star-forming regions in space. It's designed to really do way more observational science than we've been able to do so far. And one of the other good things about a telescope like this, it's in some sense a very general purpose instrument. So almost inevitably there will be things that are observed and seen that were unexpected. And so there's also just an exploring the unknown.
Okay. So dark matter, are they
It will be able to study, not see dark matter, but see gravitational effects of dark matter, and hopefully help elucidate what the dark matter is. So yes, absolutely.
All right. And well, I guess we're going to capture images of planets in our solar system.
Yes, that's not going to be a primary mission, but they did have a image that they released a couple days ago of Jupiter, and it's extremely exciting for even people studying near Earth objects like Jupiter. The main thing is to look farther in space, but it can also observe our solar system planets in a way that we have not been able to do, because it's looking, again, at different types of light than other telescopes.
All right, so when I was kind of researching myself to try to see what the difference between the Hubble and the James Webb telescopes, one of the things they were talking about was infrared.
Yes.
So, and from what I understand, the Hubble telescope, in a sense, is like the regular telescope in which you can see visible light. And the James Webb is going to be able to get to the infrared.
That's
And
right.
so what does this all mean, and
Right.
how is this significant?
So light is a type of what's called an electromagnetic wave. So it is a wave, and a wave has things that oscillation. Think of just when you're at the beach. I know you were recently near water, so waves go up and down, and they have a wavelength. So how far one peak is to the next peak. So light is like that too. It's not a water wave, it's an electromagnetic wave. What we see, what's called the visible spectrum, has a certain range of wavelengths. There are shorter ones. The shorter ones are blue, and then it gets into the greens and yellows, and then the longest ones are red. Okay, and that's what we can see. But the different types of waves don't stop once it gets out of our visual spectrum. It goes in for the shorter wavelengths, it goes past the blue into what's called the ultraviolet and into a whole bunch of other waves. And then on the other side, it gets past the red and gets into the infrared. So these are just longer wavelengths of light than we can see. Actually, other animals can see into the ultraviolet and into the infrared. So for instance, snakes can see into the infrared, so they can actually pick up where things are by the heat that is being emitted by animals. So that's one thing that snakes can do. And there are bees and such that can see into the ultraviolet. So animals can see that, we can't. That's just how we evolved. So the Hubble telescope could basically see the visible spectrum. It could see a little bit into the ultraviolet, it could see a little bit into the infrared, but it basically followed what our eyes could see. The James Webb Telescope was designed not to see the visible part of the spectrum, but to see mostly in the infrared. It can see a little bit in the visual, but it's mostly in the infrared. And the reason for that is when you're looking way, way back into deep space, the light that was emitted there, as it has traveled to us, it gets stretched out because the universe is expanding. So the light itself gets stretched out. And so what was in the visual spectrum, say, gets stretched into the infrared. So Hubble was unable to see light that had started way, way, way back in time and has stretched into the infrared, but the James Webb Telescope will be able to see that. And that will allow us to see deeper into space, which means further back into time.
All right, so when we talk about further back in the time, it's just, I mean, I know we've talked about this, but I mean, are you really serious? Like literally speaking, we are able to see back in time, like yesterday, a week ago?
Yes. So
13.8 billion years ago?
Yeah, so that's the idea. So the light that was emitted from these images was emitted 13 whatever billion years ago, say 8 billion years ago. It depends on what image you're looking at. It was emitted a long time ago, and we are seeing that light now, but the light we're seeing now has been traveling for that length of time. So what we're seeing is something that was emitted, and so we are seeing something that was 8 billion years old.
Okay, all right. So when so, you know, going back, the Big Bang, there was light gases or light elements that were initially here, and then heavier elements came about, lithium and all that. And so by doing this, by being able to use the James Webb Telescope, using infrared, we're going to be able to see better how galaxies form, how stars form, died, and all that kind of stuff.
Yeah, so the hope is to see really the very early light emitting objects. So the earliest stars, the earliest galaxies. And, as you are observing, you'll also see things that are younger. So you can help paint a picture or make a movie of the history of all of the universe, much more than we could before. I mean, we were able to do this before, but we could only see so far back. And now we're going to see further,
Okay.
among other things.
And so one of the things that we taught, one of our episodes, I don't know, I think we've had maybe 12 or 13, we talked about the discovery of exoplanets or planets outside of our solar system. And so is the James Webb Telescope going to focus on that? I mean, my take on the whole exoplanet discussion was that, when I was a little boy, I was like, is there life, elsewhere outside of the universe, outside of Earth? And it was kind of like, oh, no, of course there's not. That's ridiculous. That's just science fiction or whatever. And then the exoplanets were discovered. And now there's more hope that maybe there is evidence of life in one of these exoplanets, for example. So is that going to be part of the mission of this telescope?
It will be. So one of the things that it will be able to do is look at exoplanets. So these are planets circling other stars, and try to figure out, it will be able to observe essentially what's making up the atmosphere. Is there water there? Is there oxygen there? And from the chemistry that we know, there are certain things which are present in atmospheres of Earth, really, that is caused by life. So the fact that we have oxygen in the atmosphere is due to the fact that we have plants all around the Earth. So if we could pick up a telltale signal like that from another planet, and there are other chemicals that you can try to pick up, if you can see that in the atmospheres of other planets, that would be a very strong evidence that there is some type of life around those planets. And so this is one of the things that the James Webb Telescope will be able to try to do.
All right. And so the images that we're going to look at today, I know one of them is going to be an exoplanet.
Yes. The spectrum from an exoplanet, they were able to get and pick up the fact that there is water in the atmosphere of this planet.
Okay. And we will look at that image of that exoplanet and discuss that in a little bit more detail, but I just want to sort of give a little bit of a preview. All right. And so I guess the last part of my introduction here is that what's interesting to me about this whole mission is it's not just America, it's not just NASA. You have the European space agencies, you have the Canadian space agencies. And from what I'm reading, anyone can apply to use this telescope.
In principle, that's right. It is a public instrument. It was, NASA funded instruments are, you can go and apply to do certain types of observations. And then also the data that it collects, the pictures and such, are made public. So it might take a little bit of time for them to release it, but they try to release it within 6 months, I think, of all the information that the telescope will be gathering. So you can either apply to actually have it point and look in certain areas, or you can also just go and grab the data and analyze it yourself if you'd like.
All right. So let's just say I wanted to apply. I mean, I'm not going to do it, but let's say I wanted to. Where do I go? Is there, back to the James Webb NASA website?
There's NASA has ways for you to submit basically an application for this. So you would go onto the
portal,
basically the portal, and put in an application. Yeah.
All right. So I'm going to be dropping a lot of links here, for the launch, where the telescope is now and all that kind of stuff. And I'm out, after I do the show, I'm going to try to find out a link to the application in case somebody out there wants to actually do it. I also read somewhere that there's some like 3D modeling on Instagram that any of us can do. So I'm going to research that also and put that link on the show. I don't know if you read about that, but I saw some reference to that. Okay. I think that, all right, the last thing I want to say, all right, no, actually I did it. All right. So let's go to the images now. I know that they were going to drop all the images at once, and then they decided to do the initial one and then 5 following that. And I know you mentioned um, uh, which planet? Not Jupiter.
They
Are you going to be able to show us those images as well?
yes, I can
Okay.
show that now.
All right, so let's take over. Let's show us
right.
what you want us to and talk, and you do the talking.
So let me first say that we are taping this on Sunday, July, what's the date today? 17th. The first images were released. The first image was released on Monday, July 11th, in a big press conference. And that's the image that we're looking at here on the screen. So if you're watching the video link to this, so it is called a deep field image. So what they're doing in this is holding the telescope at one point in space and doing a very, very long exposure. So you think of a camera, you open up the lens and you look for a long time. What does that do? That allows you to collect more light. So if you're taking an image at night, you open it up and you can see the bright stars, right? This is a similar thing, but you're looking in space and with a very, 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 very good camera.
Yeah.
And so what we're seeing are tons and tons of very, very, very far away galaxies. All these little dots, essentially, most of these little dots, I should say, are galaxies that are really, really far away. There is a galaxy cluster in the center, and that's sort of the bright light that we see in the center here. So there is a closer up galaxy cluster. So there's lots of mass in the center region here. And then behind it, there's lots of other galaxies. And one of the things that you can see are, it looks like some of these things are stretched out into rings almost, or arcs. And that is due to the gravitational lensing. So the fact that there's all this mass between the galaxies that are behind it and us, the gravity causes the light to bend and you get these arcs. And so that is one way you can actually see or tell that there's a lot of mass in between. And it also allows you to calculate where all that mass is and how much of it there is. But the main thing is that we're seeing galaxies that are really, really far away, and it's actually much farther than we could do otherwise. Seems like I got kicked off, which is odd, but okay. Let me join back up so we can put the image back up.
And as you're doing that, one of the points that you just made, gravitational lensing, and that has to do with, does that support Einstein's theory, general relativity?
Absolutely. So these bending of the or the stretching out of the stars, they're called Einstein arcs. If you are perfectly well aligned, you'll get an Einstein ring where the light from the star is directly behind the mass, and you can actually see a full ring. Those are very, very hard to find, but they have found a few. And this is something that Einstein didn't think we would actually be able to observe, but it was one of the things he predicted way, way back when, about 100 years ago. I do not know why I cannot reconnect. Might want to.
All right, back on planet Earth. We just we're talking to Dr. Leibovich about the lensing and Einstein's theory of general relativity and gravitational lensing. I got that right?
You did.
Okay. All right. So this image, I mean, was it just like, all right, let's just point the telescope in a random spot and take the image, or do they have like a particular reason why they chose this particular spot?
So they were looking at this particular cluster, galaxy cluster, which is called SMACS 0723. I mean, that's just the name of it. But they were also looking at this for a very, very long time so they could see all the faint galaxies behind it. And this is something that Hubble did, and was one of the most profound images that Hubble did. It was called the deep field image, where it would take a image and look at it for like 12 hours straight. And that allows you to collect a lot more light than you would be able to otherwise, as I was saying before. So the James Webb did this as well. They didn't look nearly as long, and they were able to see more galaxies deeper because of James Webb Telescope's capabilities are better than Hubble's. So they will continue to do this. They will look at deep points in space. It's a tiny little speck of the sky. The paper was saying that, it's like a grain of sand an arm length away. That's how small the spot is on the sky that it's staring at. And James Webb Telescope will continue to do this. It will look probably deeper at this point, but it will also probably do other deep field images. And one of the things this allows astronomers to do is to figure out how many galaxies there are in the universe.
Yeah.
And because they can see more that are further back. So,
All right. So in each gallery, so every little dot I'm seeing here is a galaxy?
almost every single dot. There's a couple, the ones that have these 6-pointed, these are probably foreground stars. That's why they are not quite in focus. That's what the lines are doing here. And then this is the center point here is the galaxy cluster itself. But most of these things are galaxies that are way, way far away.
Each galaxy has billions of stars, planets, dark matter.
Yes.
So each one of these little things that I'm looking at, for the most part, except with the exceptions that you just gave me, have billions of stars.
Correct.
All right. Wow, that's fascinating. All right, so let's move on to are we ready to move on to
Sure.
the next image? Let's
Sure.
do
Let's
so that was
go.
day one. That was Monday. The president came out, revealed that image.
Yep, I got it. Okay, so then the next day they released a number of images. It will take a second to load up.
Okay, beautiful.
There we go. I
All
just
right.
had to go. And so this one here is a nebula. So when stars essentially blow up, they emit gas all over the place. And this can cause new stars to form. And this is a place where new stars are forming. So around the edges here, you can see some bright stars, perhaps, so the little bright dots. And this is basically a cloud of gas, which is spreading out in the universe. You see these streaks, these light blue streaks that are coming up. That's actually ionized gas, which is getting emitted from this cloud due to new stars that are forming. They're forming new stars, they're ionizing gas, and that gas is getting blown away. So this is, other than the fact that it's a stunningly beautiful and amazing type of image, this is something that astronomers can study to look at star forming regions in the universe. Another thing that the James Webb Telescope is allowing them to do is see a lot more detail. If you look at the same image, same image from Hubble, it looks basically opaque. You can't really see into it. And the Webb can actually see into it and see what's going on inside. So it can see these star forming regions better.
All right, so going back to the infrared, we can't see infrared, some animals can, this telescope can. So is the image, how can we see an image containing
Gotcha.
stuff from infrared
Excellent
if
question.
we cannot see infrared?
Yeah, that's a great question. So the images have been shifted in color from the infrared into the visual part of the spectrum so that we can observe it. If we were looking at this directly from the telescope, it would look black.
Yeah.
Essentially. I mean, there would be dots where stars are, but it would basically look black. So what they do is they essentially shift the spectrum from this infrared into our visual range so that we can observe it. They also want to, increase the contrast without oversaturating the pixels. And so there's actually a fair amount of image processing that goes into all of these images. But that's the basic answer. They're shifting it into the visual.
Okay, now being the lawyer that I am, when I'm hearing image processing, tell me how confident you are that what we're seeing here through this processing is an accurate depiction of what we are being told this is.
I would say that I am very, very confident because I know some of the people who work on these telescopes. And it is sort of a standard way that they are turning data that we can't observe with our senses into data which we can observe. So it is this sort of a standard scientific practice. It is true that if we were looking at this with our own eyes, it would not look like this at all.
Okay, and so we had the first release, the first image was on Monday night with the president. Now, this is 3 days later. They're releasing 5 images. This is the first of the
This
5.
is one of them.
All right.
So we can go and look at another one. This one is called Stephan's Quintet, which is a number of galaxies which are bound together. There are 5 galaxies you can see. So there's 1, 2, 3, 4, and 5. The one on the left, it's really only 4 that are bound together. The one on the left is much closer to us than the others. So it's not actually gravitationally bound together, but its position in space looks like it's part of the 5. The other 4 are actually bound together gravitationally. And one of the things that other than the fact that it's a beautiful image, again, is you can look at how the gas is swirling around these and how these objects are interacting. So this will allow astronomers to learn more about how galaxies collide together and so on. So,
Yeah. So we knew where Stephen's Quintet. It's not like this
it's
was
not
just a
new.
random.
In fact, this was shown in It's a Wonderful Life.
Okay.
And so it's not at all
The movie.
new. Yes, the movie.
Yeah.
It's not at all a new discovery on objects in space. However, we're able to see it in much clearer detail. The galaxy, the gas swirling around the galaxy and so on is much clearer than we could see with other instruments.
All right, so let's move on to the next one.
All right, let's move to the next one. So this is an Southern Ring Nebulae. And if you look in this first picture on the left, you can see a bright spot in the center. So that's a star. And what you can see on the right is you can see actually there's 2 stars there. So you can actually image the fact that there are 2 stars orbiting around each other in this nebula. So what happened a long time ago, star exploded, gases go flying out into the universe. And there's star in the center, remnants essentially of what caused the explosion to begin with. And this is just, again, a stunning image that they were able to capture.
All right, and so my understanding is, so these 2 of the 5 images that we've seen so far were nebula.
Yes, that's true. They were, yes.
And one of the images shows a star that's actually dying. Did I get that right?
Did they? So they were stars that exploded in the past. There's things that are still there, remnants from that old stars.
Yeah.
That often happens when a star explodes. There could be something left over. It could be a black hole. It could be a neutron star. It could be a white dwarf. So these are sort of the ashes of the universe. So after these things explode, there are things that are left over. So those are things that we can see.
Okay, let's move on to the next image.
All right. So the last of these ones is the spectra from an exoplanet. So we're not actually seeing the exoplanet here itself. What we're seeing here is the different wavelengths of light that we can observe essentially from the atmosphere of this exoplanet. This exoplanet I can't remember how far away it is, but it was far away. It's in our galaxy. So all the exoplanets we know are in our galaxy. They're about 5,000-ish, more than 5,000 that we have observed at this point. This one is a gas giant, so it's sort of like Jupiter. It's smaller than Jupiter, I think about half the size, but it's much closer to its star, and so it is much hotter. And because it's hotter, its radius is actually bigger than Jupiter, even though it has a smaller mass. And what they were able to observe here is that essentially some of the components of the atmosphere. And so they were able to observe water in the atmosphere of this planet, which as we know of life on Earth, water is a key component. I mean, it might not be necessary elsewhere in the universe, but for what we know, water is key. So observing water on exoplanets is one thing that we want to see, or we think that is necessary for life. Okay. So there's not going to be life on this planet. It's a big gas ball.
Yeah.
But just the ability that they were able to see this quickly with Webb is a great sign. Hubble was able to see it, water, but it was much harder. They had to stare longer and so on. So now they're going to be able to do these much better and quicker. That's
All
the
right.
hope.
So they're going to be able to look at all, you think they'll be able to look at all the exoplanets?
I don't think they'll be able to look at all of them. That's a lot, and
Yeah.
they're constantly observing more. But what they will do is pick ones which look interesting, whether they are ones like this, where they could, because of the properties, feel like they could easily observe the atmosphere, or more interesting would be planets which are in the Goldilocks zone, which is the zone of size and in comparison to this type of star that they think life might be present. That would be the ultimate goal, because that's the ones you think life might be present.
All right. Yeah. So that's like the most likely place that they could find if there is other life.
That would be the ones that they would hope. Yes.
All right. And so from what I understand, this exoplanet is WASP-96b.
That is correct.
All right. Let's move on to the next image.
All right. So the other image that we have here on this web page is the deep field image. So let me see real quick. We go to James Webb Telescope here and we go to images. We can also show the images of Jupiter. So here's the images of Jupiter, and it is very, very bright, which means that they're capturing a lot of light. You can actually see one of the moons, I believe that's Europa, and you can see it in different wavelengths. So what you're looking at in this picture is using the different cameras that they have on there. You can look at different parts of that infrared spectrum. And so you can see in one spectrum, it looks like a big orange blob. Another, you can see the bands and the red dot. So these are some of the things that you can see using the telescope. So this is not, necessarily the image of Jupiter that we are used to, but as you said, it's looking at it in the infrared, which is not what we see. So we're used to seeing more of the visual spectrum.
Gotcha.
So this is sort of the infrared version of Jupiter.
All right. So do we have any other images that we can show?
I think that's pretty much it at this point. I don't think that they've released any more. So the first images dropped on Wednesday. All of the images, on Monday, all the images that they've presented were basically taken during what's called the engineering run. When they're setting up the telescope, making sure it's working, they're taking a few sort of test images. So these were all test images, essentially. Now the real fun begins, because now the real science will start, where they'll do more of these type of things, but also look at other things which are interesting to astronomers for one reason or the other. So we will start to see more and more images come out. But now that we're actually in the science run, it's going to be amazing.
Amazing. Yeah. I'm amazed. I really am. I didn't think I thought it was going to be like a big deal, but it really does seem like a big deal. All right. So obviously the scientists there are focusing on certain things.
Yes. I mean, there's different things that are like already planned, have been planned for a long time to look at, a number of different objects to look at, areas in the sky to look at. And as time goes on, there'll be more and more proposals that go in to look at different things, and images will keep coming out. So.
Have they released what it is they're actually focusing on, and what they've decided to look into? Or
Yes, I mean, I don't know if there's an easy way to get that, but the proposals that are been accepted are always public because it's a public, a governmental institution,
yeah.
agency. So those are public. I don't know if it's necessarily easy for the general public to see, oh, what's it looking at next. I don't know if it might be, they might have a public version of what's next, but I just don't know.
Okay, and do you know whether they've released a date when they're going to release the next images, or is?
I don't know if they have said that yet either. So
Okay, all right. So I think that pretty much does it. Is there anything that we didn't cover that you think,
I
we
think
should
we
discuss?
pretty much covered it. I mean, it's a fantastic instrument. We should just be amazed about the scientists, the huge number of people who participated in the building and commissioning of this instrument. We should be thankful for Congress for funding it. There were cost overruns, there were delays. I mean, some were COVID, but there were delays before that. And they were continuing funding, and we're going to start to reap the benefits now. So we should be thankful for everyone involved.
All right, I think that does it. Dr. Leibovich, thank you for coming on today.
My pleasure.
And helping me and everybody else understand what we are seeing. And it's a very exciting project. And I guess who knows what we're going to find out
Absolutely.
about
That's
our
right.
universe.
That's right.
All right, that'll do it for this episode of Cut to the Chase, everybody. Have a good day and take care.